The part 2 and part 1, we were mostly focusing on how to work on VMD, how to merge PDB, that is a protein file, as well as a ligand file. When you have taken it from the doctor complexes, how to set the parameters, force fields, how to generate the parameter files for ligands using online servers, and few other things. So from the third part, we are going to look into how to perform the molecular dynamic simulation using NAMD, both in CPU as well as in GPU. But before going into that, since it's already 5 months, I'm sure there will be a lot of updates happened with NAMD as well as a few other parameterization tools. So let me give you a wrap up about those updates, because right now, if you're going to work on NAMD, probably you'll be downloading the latest version. So let us go through that. So whatever you're seeing on the screen now is the YouTube channel, and there are a few other things also coming up, including GROMACS, to work GROMACS and GPU in Google Colab, and there'll be a new Colab notebook also coming for, including conformer generation, virtual screening, minimization, and protein ligand optimized molecular dynamics, including binding energy calculation, everything in a single notebook. It's tested, it's working, but still things has to be put in a proper way so that anybody who reads it will be able to understand it. Moving forward, all the configuration files and supporting force fields and parameter files will be available in my GitHub. So if you go to my github.com/giribio, go to this MD notebooks. Inside MD notebooks, you can go to NAMD, and then you can go to parameters folder. There you will have all the files. Charmm 36 files will be here, and then scripts for maxmin, which we are going to use today, and merge PSF, which was used in the last tutorial, and minimd.namd is the config file which we are going to use today for minimization, and few other top files which will be useful for NAD, then ATP, and others. So there are a few queries raised up. How do we handle cofactors if it is there in our complex, right? So that will be also addressed in the next part, but the data files are all available. And if you wanted to go with the binding energy, which will be also covered in the next part, there will be 8 series of calculations that has to be carried out in order to perform or calculate binding free energy. So those configuration files are also available. Yeah, but don't use it right now. There is a method and few input files has to be created, and which we will look into it. So in order to download these files, of course, you can download the whole MD notebooks. So here you can go to code and then click on download, zip the whole files, everything will be downloaded, and then you can extract from each of the folders. So that is all about the input files that is being used here. The next one is NAMD. I'm using 2.13 version, right? It's slightly old. This one is the version that I'm using, which was 2018 version, because that was told to be the stable version. But right now you have a 2.14 version, which is being released last August, and we also have somewhat slightly latest version with 2.15 alpha version also. But I highly recommend you to go either with 2.13 or 2.14 versions. Keep in mind, if you have multiple CPUs or cores in your laptop or computer, go with multi-core, either Linux 64 or Mac OS x86 64 or Windows 64. If you have a CUDA cores enabled the GPU cards, then you can use multi-core CUDA, Mac OS, this one CUDA, as well as Windows 64 CUDA. But then if you wanted to go for a little bit more advanced molecular dynamics, which I will discuss in the next part, then you have to go for this NET LRTS. Specifically, you have to go for that, including Mac and Windows. Yep, this one, MPI. But mostly it is Mac and Linux is what is being supported there. Anyway, that we are not covering, but we will discuss about that in the next part. So if you want to download, as I told you, multi-core is that what you can go for, or the Windows one, or even the Linux one. Today I will be discussing about both the multi-core, that is CPU based, as well as GPU based. Then last time when I did part 2 in Charmm GUI, there was no user account login. You can just simply go and upload your mol files and create the parameter files. But things have changed now. So you have to create a user account, and keep in mind it should be an academic email address. So personal email addresses mostly don't work too. So keep in mind you need to have an email address that works well for academic purpose, and that's where the Charmm GUI works well there. And similarly, you have again general Charm general force field. This also can be used, but yeah, this is something general still, so still you can use that. And then you have something called LigParGen, which we discussed in the part 2. This also can be used for generating force field, but the only difference is you cannot use it for NAMD as of now, because here they use OPLS force field. So you need to have the open source OPLS force fields to be parameterized for it to work with NAMD, but for GROMACS, of course, you can still use it. Now, it is being clearly mentioned about the Charmm GUI as well as the Charmm general force field, its usage, where it to be put, and its parameterization. Everything is being explained in this particular website, where even the latest version of this website is this one, where you can download the force field. In most of the packages, you will be finding the old version of Charmm. Usually it could be 27, I think. Yeah, 27. But the latest version is that is something called 36. Even you have gone till July 20th. So please go through this to have a better understanding about what kind of macromolecules or what type of elements or atoms is being covered, and accordingly download those parameter files of the force fields that to be used for your NAMD as well as for GROMACS. So please, it's not a one-click job. So keep in mind, you have to read carefully for which force field to be used for what type of atoms or what type of molecules that you're having. So keep that in mind. One way is download everything, use everything, but still there should be, you have to keep in mind about the compatibility, right? Now, coming to the final one, we have to prepare a NAMD configuration file. Even though the configuration files are available, I have taken it from the web. It's not that I created it myself. No, most of the files, like configuration files, everything is taken from tutorials or from other literature paperwork or from other tutorial or other from NAMD or from other specific workshop tutorials, and then we customize it accordingly as per our need. So these links will be given in the description once we finish this video. So this we talk about what are the input files that we have to give. Basically, main two input files are the PSF and the PDB file. Last time in the part 2, we covered how to create a box, how to ionize it, how to solvate it. So the solvated system, we are going to use it for the minimization or simulation here. And we have to set the temperature and whether, and also how to continue a run. For example, if you want to restart or continue from that, which I'll be discussing. And if you want to give specific configurations for the restart files and what should be the restart input files that to be used, which I'll show you in the NAMD configuration file, and what are the threshold, how many steps, what kind of force field parameter that has to be used, which is very, very important. And then you also have to specify by Charmm and then cutoff values. And also we can define the integrator parameters like time step. So usually we give 2 femtoseconds per step, and then you can take it to 100,000 or 10 million or 100 million steps that you can define. So that's where we calculate how much nanoseconds the calculation have actually run. In fact, few of them asked me what is calculation for the time step and nanoseconds, which we will discuss in the next part. And then if you want to define about the Langevin dynamics, which balances the friction with random noise to drive each atom in the system towards a targeted temperature. So if you want to maintain a constant temperature control, so that can be thermostat. And then to define the periodic boundary condition, that's where we are using a script where maxmin script will be used, but that's where it also comes into the picture. And then regarding the wrapping the water, and then also we are giving partial mesh evolved, which is the full electrostatics, which are more accurate and less expensive than the larger cutoffs. So these also will be giving. Then constant pressure controls, then Langevin piston again. We are to control the target pressure and dynamical properties of the barostat, right? Accordingly, if you want to fix specific atoms, if you wanted to, you can do that, or interactive MD features. And finally, this is something which we define it everywhere: how many steps, how the lower potential energy for 1,000 steps to be considered, and the minimization zero velocity is how to be considered based upon the temperature. And this is how, so please go through this before using any NAMD configuration file. I know it is easy to copy paste and use it, but try to understand what you're trying to do. Now let's go to the configuration file. So this is a configuration file that is being uploaded to the GitHub also. Don't worry about this path and all. I'll tell you where you have to put this. So my input file, the coordinates is solvate underscore protlig.pdb, which I have created from VMD. Please refer to the part 2 so that you will be able to understand how do we generate this PDB and PSF file using VMD. Right, and then these parameters are all the particular force field files that we are defining. So I'm trying to cover proteins, ethers, then Charmm general force field, carbohydrates, lipids, even water ions as per NAMD parameterization. So these all things are being considered here together. So it is very important that you give the path correctly. And this particular one, topologies.prm, this is what we have downloaded from Charmm GUI, because that is where the parameterization done for our ligand. So the parameter file for the ligands is lig.prm. So if you can mention these path properly, there shouldn't be any challenges on the parameterization. Then we are trying to say, for example, if you want to restart a job, so the same configuration can be used for restarting a job. But for that, two things are very important, because the coordinates and structure is not going to be reused, because if you're using that, it will start from the beginning. I wanted it to start from where it crashed or where it stopped. So here, if you see here, so when you're trying to restart, you're replacing the coordinate and others with this minimize.restart. So keep in mind, if you want to restart a job, these are the files that to be used. Otherwise, you will be starting from scratch. Then you wanted to define your output. To get your files organized, it is always to save your output in a separate directory. And keep in mind, you have to create that directory before running a NAMD. So I have created a directory called CPU, and then within that directory, I give CPU slash, and this whatever name you're trying to give here, that can be replaced here. Okay, I just gave output, so all my output files will be having output. Then you're trying to define certain other parameters, which I have already discussed a few minutes back, and then about the requirements of Charmm, simulation space partitioning, multi-step first time step and other time step, I'm giving 2 femtoseconds, and then I'm setting the temperature, and then Langevin dynamics again for the temperature constants. Then PME is being designed, right? And then a few other group pressure and other parameters being set. Now comes a very important part. Where do we get this periodic boundary condition? So that's where we have max min script. So let us go and find that out. It is already there in the NAMD website for the under the plugins, TCL scripts. Otherwise, I have also uploaded it in the GitHub. So let's see how to use that. Let me go back. I'll go here. Okay. I'm sure I want to just make sure that you're able to see the text properly. I just made it slightly bigger, right? So here, I'll go back to this. Yes. So I have all the files here. All these files I have generated last time during the part 2, but I want to show you a few things which I will discuss now. So let me show you the script which is called maxmin. So this is the script that is maxmin available. Don't try to see and type it. It's a bit lengthy. So it's better that you download it from the GitHub and then use it. So this works with the TCL SH. So let me tell you, whatever that I'm showing you, the commands in part 1, part 2, part 3, and further, all are in par with Linux commands. It works with Windows also, but make sure the those commands are a bit different. This exactly works with the Linux as well as Mac terminal, but when you go with Windows, it's slightly different. For example, here I'm listing the directory content by giving the command ls, but in Windows it is dir. If I want to rename, there it is ren or rename, but here I can give mv. So make sure that you are aware about the basic commands of those command line as well as Unix command lines. Okay. Now, how do we run this? So wherever you have generated the files, for example, my basic file was one STP. One STP is the example that I have taken, which has biotin as the ligand. I loaded it into VMD. This is what I'm trying to tell about part 1 and part 2. I loaded into the VMD and I separated them, one as protein. Here you can see protein, and then I separated another one as protlig as my biotin, which is the ligand, co-crystal ligand. Or if you're taking a docked confirmation, the docked pose is the ligand and then your actual protein. And then this protein protlig I converted to mol file using or lig.pdb, and then I converted it to lig.mol using OpenBabel, and then I uploaded it to Charmm GUI, and then I able to download the parameterized file like ligand rm.psf, rm.pdb, INP, and str, then including PRM file, which is there in the topr file. After that, I have to combine them. So I used this particular script called merge psf.tcl. I used this script to combine my ligand of parameterized file and the protein parameterized file. So protein parameterization is being used using VMD. There is an option called PSF generator, auto PSF generator. Using that, I generated for proteins. Later, using this particular script, I combined the protein auto PSF PDB and PSF and PDB file, as well as ligand RM PDB and PSF file together to call them as a protlig file. So I correct myself, protlig, which I told you earlier, is for the complex, but ligand.pdb is what I separated the co-crystal ligand. Sorry about that. So after merging, I created a protlig.pdb and protlig.psf file. Then I use this file to ionize. It is using again VMD, and then finally I solvated it again using VMD. Please refer to part 1 and part 2. So after the solvated structure, this is what is my input files. The Solvate, Protlig, PDB, and PSF is my input file for my further minimization using NAMD. So far, I did not use any NAMD calculations, only just used VMD to generate all my required input file and to form a complex. So let's execute the max-min in order to generate the periodic boundary parameters that we have to put into the configuration file. So in order to run that, make sure that if you're running Linux or Mac, you have to install TCL-SH software or a package in order to run the script. Otherwise, what you can do is please refer to the part 2. You can go inside VMD and open the TK console. From there also, you can run the TCL. In Windows, you can do that. So please refer to the part 2 to look into that. I'm not repeating it, otherwise the video will be further lengthy. So here I'm just running TCL and TCL-SH, and then I give merge, max-min. I just used autocomplete. Max-min TCL, and I just press enter. Now it is asking me which PDB file you want to consider in order to calculate the periodic boundary parameters. So as I told you, the final structure, the system that I'm having is Solvate protlig.pdb, right? You give any name you want. I'm just making you understand. So it's not necessary that you have to give the specific name. No, your favorite names, you can go ahead. And then I give enter. Keep in mind, we want to consider all the segments. What all we have added earlier in part 2 and part 1 we have discussed. You have proteins, you have water molecules, you have ions, as well as you have ligands. All these we want to be considered in the periodic system. So we give segment as all. I want all the segments to be added. I want all the residues to be considered. I need all atom type to be considered, and also nothing greater than or something, but I want all here and all. And so now here it has created my particular periodic boundary conditions. So this I have to just copy, right? This I have to just copy and then paste into my NAMD configuration file. So easy, right? So this is what you try to do. I have already copied it here. You can see the same values. So 48, 37, 53. 48, 37, 53, right? So already I have copied. So for your system, this is how you have to copy. If you don't do this properly, the minimization will break and you will have a lot of errors generated. So be careful to do this step, and this is very much mandatory. Once you copied it, just save it. Okay, you can do this in Notepad. Don't use Notepad if you're using Windows. Try to use Notepad++, or even Atom text editor can be used. Do not use Notepad, or also don't use WordPad. Okay, great. So we are done with all the preparation of our parameter files. Now let's also look into a few other things. A little bit of organization is required. So I told you, so MiniMD NAMD file is there, and we have all the other, the protein Solvate Protlig and Solvate Protlig PSF and PDB file is here. Now let me show you a few other files. Topar. Topar is a folder that you will get when you download your Charmm GUI data. This is the Charmm GUI data when you get. So when you extract it, this is how it looks like. So your ligmol is here, then your this is where the files I have taken for the ligand parameterization. So ligand RMPDB PSF file, STF file, which I copied and pasted in the previous folder. And I just copied this topar folder to make the path much more simpler. I just copy pasted here, that's all. Another thing very important is Charmm topar file, because I want all the force field parameter files to be in the same folder. Again, just for convenience, right? You can put it anywhere and give the path, but just for convenience, I'm using this. You can even put it in VMD folder, or you can put it in NAMD folder, no problem. But for convenience, I'm putting it in the same folder. So you need to have just an understanding about the path, how to define. If it is in the same folder, how to define that. If it is in a different folder, how to define or call that. Those basic understanding of DOS as well as Unix or Mac terminals is very, very important. Right, so that's all organizations require. After that, I generated a folder called CPU because I'm going to show you two different calculations on CPU and GPU. And I will tell you the difference here. On GPU, the same calculations when I did, the calculations finished within 20 minutes. When I did it on CPU, let me check that first and let you know before we proceed. Let me see if it is CPU. Yeah, tail CPU.log 3943. Let me calculate how many minutes is that. It took about 1 hour, 5 minutes. So I ran this calculation on 12 CPUs, right? It took 1 hour, 5 minutes, but same thing on a GPU took only 20 minutes. That's a difference between a GPU and CPU. Don't worry, I know many of you might be using laptop and you cannot you make use of GPU. Don't worry, you can still look into CPU. Anyway, now let's get into the job. So I created a folder. I went inside CPU. Okay. When I looked at, no files will be here, but how do I run the job? Now, before defining this SOFT or NAMD, usually how do we give the job? Usually the standard thing is, let me show you that and then I will go and explain it. Usually we give NAMD2, that is the package name. Then we have to define how many number of cores to be used. In your case, if it is only 2 or 4, just give plus P2. In my case, I give 2, 8 or 12 or 16. And then I have to give my configuration file, which is for the NAMD that I have prepared. And then I will give a space and greater than symbol and space, and I give a file name .log. Very important, because this log file is what we are going to use to plot certain things, including energy, temperature, bond, etc. So this log file is very important. And I give an ampersand symbol so that even if I close this terminal, the job does not get interrupted. Now, in this case, if you want the NAMD2 to work in your directory, that is called working directory. That's where my files are there. That's called working directory. If you want NAMD to work there, you have to set systems environments. In Windows, it is a different way to set the system environment. In Linux, it is slightly different. So let me show you in Linux and Mac, but in Windows, as I told you, you have to go to the systems settings, then click on the advanced and then system environment variables. And there you have to set what is called NAMD2 and give the path. In Linux or Mac, what we are going to do is we just give alias, then is equal to, and then I can say home, whatever path, GiriBio slash NAMD slash NAMD 2. Of course, I have to say alias NAMD2 is equal to slash home GiriBio NAMD2. That means if I just type NAMD2, the machine will understand the path is this one. Imagine if you're using Windows, I understand there will be spaces between your folders and should try to use double quotes from the beginning and the last. So for example, you put a double quote here, and then if I give GiriBio space computer, if something like that. And sometimes you have to give a double quote here also. So it depends upon the DOS prompt that you're going to use. Anyway, and then if you want to give a path, that's what we are going to use here. If I say I want to minimize my path, soft is equal to slash home slash GiriBio slash softs slash packages. So if I give this, I need to give only soft rather than giving all this path while I'm typing. So these are the certain advantages. Okay. Now, let me go and give the data here. So number one is that I have, in order to run the job, which I have already explained, in your case, if you set all the environment variables and everything, this is the way. And you need not to give this dot slash, right? This is the standard command. Why I gave and all, I already told you. My files, everything is in the folder called the demo. My file is everything is in the demo, but I created another folder to get it well organized. So I created a folder called CPU, and I'm trying to run the job within the CPU. So when I'm trying to run the CPU, I want all the files also to be saved in the CPU. Hope you remember in the configuration file output I gave CPU slash output. So that's why all the output will be saving here. Another thing, since the folder minimd.namd is outside of CPU, I'm just giving double dot slash so that it will go take it from outside. And the full path I have given in $soft. This works for Linux and Mac. For Windows, you can give the full path directly. And then I gave NAMD2 plus P, where I have to give my number of cores that will be used for calculation. And then I give my configuration file greater than symbol and CPU.ly. I've already completed this calculation, so I'm not going to run. If I just press enter, the calculation is going to run it. Right? So there is a question from Thai. Yes, you're right. The protlig PDB file was taken from after combining, after merging the protein and the ligand PDB and PSF file using merge script of TCL. Yes, you're right. So after running the calculation, you will be generating all this file output.cod, output.dcd file, which we are going to use it for analysis using VMD. And then these are all restart files, which I told you already, right? So if you want to restart, if the job got crashed, you're going to use these restart files for that, right? This is what you're going to use it here. So let me show you again. So if I go to the beginning, I already showed you. Yeah, this is what I'm going to. So instead of minimized, I have to use output because that's the name I gave. So output.restart.cod and output.restart.val. So that's where if I want to restart something from here. Okay, so the same way I have calculated for using GPU also. Same files, nothing different, only the time is different and a little bit of difference in energy. So let me see tail, the log file which I gave, cpu.log. And then I just got it saying that the wall clock, CPU time, how much RAM it took, right? So it took around 67% of my GPU. I'm using RTX 2060. I didn't go for a higher end. This is okay with me. Getting a 1 hour, 5 minutes job within 20 minutes is fair enough for me. So, so I'll repeat, the GPU card that I'm using is 2060 NVIDIA card, and it's a 6 GB card. Yeah. So CPU took around 1 hour 5 minutes, and it took around 875 MB RAM. Right. Let us go to the GPU now. In order to run the calculations under GPU, let me see where's my path for GPU. Yeah, it's here. So GPU. Nothing different, all are same, all my configuration file for the NAMD, everything is same, nothing I'm changing, only changes when you're running the GPU calculation. So let me show you that. So for GPU calculation, you have to download the CUDA enabled NAMD, keep that in mind, okay? Not the normal NAMD, you have to download the CUDA enabled NAMD, which I had showed you earlier in the beginning of this video, as well as ensure you have installed all the CUDA libraries, toolkit, as well as NVIDIA graphics card drivers. So keep in mind, libraries, CUDA toolkit, as well as NVIDIA GPU card drivers, all latest, right? Or toolkit could be 10 also. Don't go for the recent one, go for 10 or 9. So that is always recommended. Otherwise, you will have a lot of issues with certain other softwares also. So then you will be giving you, so I have installed that or extracted that software into the folder called NAMD GPU. So in CPU, you can see here, I didn't give any GPU, it was just NAMD. Yeah, see, it is just NAMD under CPU, but when I came to GPU, it's I have extracted under NAMD GPU because the softwares are different there. Then the first command is charm m run, then NAMD2. Again, I have to give some amount of CPU for serial calculations. Very important. I'm not going too much into that technicality, which we will talk about it a bit later in a different session. So we have to give at least 2 core or 4 core is recommended, but at least 2 core for from CPU. And then you will give idle poll, and then you can give your configuration file, the same configuration file, but I just made a mini MD1 because I want to change the path from CPU to GPU. That's all the difference. And then I gave a output file as gpu.log. So in your case, when you run, if you have set your NAMD path properly for the GPU, this is how you're going to put. Let me type it, right? So I'll be typing as charm run NAMD 2 plus P2 plus idle poll, then mini MD dot NAMD, then greater than symbol. You can give any name, GPU or output or whatever log. This is how, if you have set your system's environment variables properly. Otherwise, you have to give the path and take everything, right? I hope you are not confused with that. You have a better clarity here. So I'm going to take the command which we were about to run. Yeah, this is the command. Yeah, one more thing I want to mention is another option is there where you can give um, an AMD P2, that is 2 core, and then if you have multiple devices, yeah, there are chances where some have installed 3 or 4 GPU cards in your machine. So you can give 0, 1 so that it will be taking multiple GPU devices for the calculation. I'm not going for that advanced. Let us think about only one GPU and then try to work on it. So I already finished the calculation. So let me show you GPU. Nothing much. That command, if you enter, it should run. If there is any error, of course, mostly the errors would be you did not define the path properly, or you did not give the output file properly. That's the only error that you can expect. Otherwise, most of the things you have taken care, because if you don't give the parameter for the force field correctly, that also will give an error saying that they couldn't find a parameter for specific residue or specific atom type. That is because you did not define that parameter properly. So make sure that when you're generating the PSF and PDB files using VMD, try to use all the possible parameter or force field parameter files from Charmm 36, whichever to be required. And keep in mind, do not use old Charmm force fields, because if you want to use cofactors, especially NAD, ATP, and all those things, and certain like Ca2 plus and certain few, not all of them, you need Charmm 36. That is the latest version force field parameter. So don't go with the old one. So make sure that what all parameterization to be used for your MD simulation. So make sure that that is also used for your PSF and PDF generation also, so that from the beginning you are very clear what to be used. So then you don't have any errors that comes up. So let's see on the tail GPU, what is the file. So here it took only 1,247 CPU time, which took only 20 minutes when compared to 1 hour 5 minutes, and it took only 375 RAM of my RAM, not of the GPU RAM. GPU RAM I saw it took only around 300 MB, right? So that's all it took, and it was very well smoothly running, right? So we have again here we have output files similar to output card and all the restart files also here. Now let's look into a little bit of analysis. But before getting into analysis, let me also give some heads up, a bit of marketing, right? Recently, I started some podcast on drug discovery research, where I was talking about specific drugs that is being approved by FDA for certain purposes, its pharmacological use, mechanisms, and whether it is being evolved from computer aided drug discovery or even molecular dynamics, and it's some kind of use cases and few other recommendations, all from literature references, FDA website, WHO. So nothing from my personal views, but mostly from multiple literature put together and being narrated. So this is available in anchor.fm/GiriBio. So each one is like 7 minutes, 5 minutes. I'm also learning a lot by making this podcast. So I hope it will be useful for you also. Moving forward, whatever we did so far to now to do this solvation for the complex, we can automate it using certain plugins from VMD. One of the favorite plugin is QuickMD. This is already there within the VMD itself. You need not to install anything separately. But the following plugins, what I'm going to tell you from now, very important for the next part of this video series, because that's where we are going to prepare the binding free energy calculation tools and plugins that to be used. So here you just, for QuickMD, you need to just download the VMD. It's already there. It does not do any free energy calculation, but it helps you to calculate the basically all the MD setup and setting up the files, analysis, all these things can be carried out using QuickMD plugin. Now, the very important one, which is very important for this series completely, is binding free energy estimator. The links are already given in the description, where you have to download this TCL script and you have to install it properly. And these links I will be also uploading it in the description, so you will have a better clarity, right? This is where we are, whatever output we got today, we are going to use this tool to generate 8 different series of calculation input files, configuration files in our next part. And this is the paper reference where you can get into the manual, which will tell you how to download this file and what are the steps and commands that to be executed in order to run. Works both in Windows as well as in Linux and Mac. So don't worry about which operating system, it works in all operating system. So they have given the path and properly, so please follow that. It works without any issues, it works. Another interesting tool is also something called VMD ICE. And this is also very much interesting. And it's published in 2010, 11, and then you have to go to this I agree techme and you have to download all these files. VMD.rc and VMD.drc. These two files are different for operating systems. TCL files does the job for data analysis after your molecular dynamics. And please go through this manual to look at how these things can be installed. So when you go through the manual, it's a PDF. It has clearly mentioned what are the steps that to be carried out in order to install this TCL. So all this will happen only after installing a VMD package. The first part is you have to install the VMD, right? After that, it will be showing you the steps how to copy and where to put, how to run, all those details will be given. So then how to access and all other things, I will talk in the next part of this video. And finally, we have something called as Cafe plugin. Cafe plugin is also again for VMD to calculate the free energy. And this also a plugin that to be installed in VMD. So there are 3 different plugins that to be installed. One is BFE, Binding Free Energy Estimator. Another is VMD ICE, which also looks at analysis. And then we have a Cafe plugin for the free energy calculations. So these all will be covered in the next. Now, let us quickly look into some of the analysis what I done with the calculation we got. Okay, just a second. Let me. Yes. So now I'll explain how I made this, but just see what is happening. I'm just going to play the frames. Whatever the red colored here, the red color is the ligand biotin. Whatever you see surroundingly certain bonds, sorry, the lines or stick-like bonds, They are all the amino acids surrounding the biotin. And another one thing, can you see some dashed lines forming in between in certain frames? I've just zoomed it very closely. Those dashed lines are talking about the hydrogen bonds. So in certain frames, the hydrogen bonds in certain amino acids, it is forming, not in all, and in certain others, it is forming. And whatever you see, this ones, the green colored ones, they are water molecules. So some interactions are having with water molecules also, right? So how did we did this? That's what we are looking at. First step is, yeah, let me show you something, and then I will do that. So I wanted to show this because this is the settings that I have done for making this animation, or to visualize this trajectories and frames properly. So under the graphical representations for water molecules, I made it as points. For protein, I made it as cartoon. And then for ligands, I made it as lines. That's what you see, the red colored lines. And then for the hydrogen bonds, I made within 4 Armstrong, the rest name within the rest name. So for example, my ligand within the 4 Armstrong, whatever neighboring atoms has to be there, that has to be displayed. That's what I did. And then I want, that is a hydrogen bond. And then I wanted to display all the neighboring atoms from the amino acids within 4 Armstrong. I can change it to 7 Armstrong, 6 Armstrong. You have to have an understanding what is the best Armstrong that you have to give. Recommended is 3, 4, not 3, yeah, 3, 4, 5 is recommended. Going beyond that, you could find some inter atom interactions, which is not acceptable. So why I want to make this, because I'm going to clean all this and start from scratch. Okay. So I'm going to, and if you want to increase a step, you can increase a step here, right? So you can see quickly at different frames. There are many more analysis inbuilt here on the complex. We want to see hydrogen bond. We want to see occupancy, how far this bond was hydrogen bond was very stable throughout the frames or trajectories. And then we can increase the speed if you want there. So here there are 10,000 frames available. You can increase the speed, and you can zoom out and see, you can see the box there in the water with the solvated state. And when I zoom in, yeah, I'm sure in your computers, if it is so slow, it won't be so easy when you're doing what I'm doing, trying to do now. So be careful when you do these animations in your computer. Animations in this movement of trajectories and others. So I can slow it, the speed, so that I can slowly see if the ligand is going out or coming in, how far the hydrogen bonds are stable. All those things can be analyzed. So anyway, I'm stopping this animation. You can click this and I can stop the play. And I'm deleting this. Let me show you how to start with it. So after opening the VMD, so by the way, once you have installed the BFE, you can see this BFE will be coming here automatically if you follow the instructions. And another thing is QuickMD. So QuickMD, once you install VMD, it will be already there. Another one is, which I told you, is VMD IC. It should come under analysis. I have not installed it. I have to. So it will come under analysis menu. Anyway, so first I have to go to new molecule. Then first I have to load my PSF file. So imagine that is my input file, right? So I have to take my PSF file, which is the solvated one, right? So solvated PSF protlic file. This is a complex. And then I click OK, load. Then I have to load my DCD files, which is either in CPU or GPU. If you have run in CPU, it should be in CPU, right? So I'll just try with the GPU, and I have to select output.dcd file. That is my file that I have to take with the trajectories, and then I open it, and then click on load. Now you can see, right? It is now trying to load all the frames, so it will take some time. Let us wait. So it is loading or loaded 4,000 frames. It is total of 10,000 frames are there. So whatever you see, the red color, it's all the water molecule. Whatever you see in the middle, the blue ones, they are the proteins. We will make it look better. Okay. So this is something looks different, but we can change that. Now we are going to graphics representation. I discussed a lot about representation in the second part of this video series. Okay. So you can go through that to have a better understanding. So the first thing I'm going to do is I'll create a representation. I'll go back to the previous one and click there. And in order to, so most of the difficulty, many people told me how to know that, how to select the atoms. So you can go to selections. Underneath you have something called chain. You can see chain. A is all amino acid, L is lig, W is water. If you want to go for seg name, you can see lig is your ligand, AP1 is your the total protein, or WT1 is your water molecule. So either I can give you a seg name WT1, or I can say chain W, that is also water molecules. Or if I go to rest name, and if I give TIP3, that is my water model that has been applied, that is also water molecule. So it's your choice how you want to choose, right? So here I can say that seg name, right? Or I can say rest name, but here I'll go for seg name. So I will say seg name WT1. That is going to me, I am going to select all the water molecule. And I'm going to say that you have to press enter, okay, after typing it. And then I'm going to say that I want it to be points. I don't want to see the water molecule very prominently. And I'll just say enter. And I'll reduce the size. Okay, I don't see. Okay, I have to delete this. Okay. So can you see that there are slide points here? Yeah. When I zoom out, you can see it is darker. So I made it very light so that I'll have better visibility for my proteins. And then I'll create a new rep. And here I will say just my protein. I want to make my protein to look like a ribbon or cartoon or new cartoon, right? So better you choose and then type. Right. So now I can see my protein as a carbon. If I want to change my color, I can change accordingly to secondary structure. So you can see the secondary structure, right? If you want to change the thickness, all those things can be changed. So my protein is being generated. Now again, I'll create a new representation, right? And then I will try, first I have to change and then change the thing. So first I wanted to change how it represents my ligand. So I want to show it like a element, and I want to see it as lines or bonds. Lines could be fine. Don't worry, it looks like that. It's okay. Now go to here and say rest name. Rest name lig. That is my ligand. Enter. Now let's see where is my ligand. It's there. Can you see this? This is my ligand, which is the doctor poses, right? So my ligand is there. I can change the colors according to type. So you can see oxygen, nitrogen and all, right? That is done now. Again, I want to see something more details. I want to see about the neighboring amino acids with this within this ligand. Second, I want to see all the possible hydrogen bonds. So I'll again create a representation, and then I will say probably type, and then I will say hydrogen bonds. And here I have to say something else. Within 4 angstrom of my ligand rest name, Lig. Now you can see lines formed, right? So these dashed lines are telling you what are the possible hydrogen bonds that could be formed within 4 angstrom between your ligand and the amino acid. I want to create another representation to identify all the amino acids surrounding it. So for that, I will say probably lines. Boom, that's where it is. And I will reduce the thickness, right, to identify which are the amino acids. The close by amino acids. If I want to see all the amino acids very close to 5 angstrom, just change it to 5, enter. You can see more amino acids coming into the picture, right? Now, again, I'll create a new representation, and then I'll just say protein. Oh, I made a mistake, right? What was a mistake? I should first say what it should be, then only I have to select the atom. So I will say QuickSurf. There are many others, Nano Shaper and many others, which we will look into it next video. QuickSurf, right? And then I will just say protein, enter. Now I can adjust my grid spacing, surface quality. I'm just keeping it low now. Of course, I can make it high. Medium is also okay. And then I can adjust my scale, right? That's where the coverage is. And then I can adjust my resolution to make it look better. No, I'm not going for that because I'm also sharing my screen in streaming to YouTube. So make sure that everything looks better. So now you can see your pocket, right? And also the ligand, water molecules, everything is visible here, right? Let me turn it around so that you will be able to see it properly. Great. So the pocket is very, very nicely visible, right? And you can change the colors and everything. I'm not going to play around with that, right? Something has good now, so I don't want to give too much. By the way, when you try to open it, it will be anyway in black color background. If you want to change it into white, I have already discussed in the part 2, go to colors, display, background, and click on white. That's it. So it becomes white. Now let's play around. I want to see how the ligands are interacting. Oh, let me turn around a bit. Yes, I can see now. But this is so fast, I cannot see properly. So let me make it right and then expand a bit more. Yes. So then I can slow my speed to see how the ligand is very much stable within that pocket. Very important, right? If your ligand cannot stay in the dynamic situation, whatever docking you have done has no meaning, because in docking, your protein is always rigid, right? But you have to do molecular dynamics. So that's the end of this particular session. And thank you so much. If you have any questions, please post it in the comments. I'll take up all the questions and address it in the last video. Or probably if something that is required for the next video, I will cover it in the next session. So within 2-3 days, I will upload the next session also. Thank you so much. Stay safe. Bye for now.